Okay, hello everyone. So in the previous video we had seen critical clearing angle with the loss of transmission capacity as a formula we have derived. We will use that in a small numerical example that I am going to solve now. So this example is actually example 11.15. This is taken from Power System Analysis Hadi's other textbook. So let's look at the problem. So the problem is something like this. There is a generator here whose direct axis reactance is zero point 0.3, followed by a transformer whose reactance is zero point 0.2, and then two transmission lines each having zero point 0.3 per unit reactance, and finally connected to the infinite bus whose voltage is 1 at an angle of 0. It is also given that the total power, that is the complex power, is nothing but the active power and reactive power. So is zero point 0.8 plus J 0.074 per unit. So this much of power is being delivered to the infinite bus from the generator through two transmission lines and this transformer and so on. The question that is asked is, there is a fault at the midpoint of this particular transmission line. So prior to the fault, there is a steady power flow of this much, and then there is a fault which is occurring, and due to this fault there will be a reduction in the power flow limit, and then when the fault is cleared, this particular circuit breaker and this circuit breaker are open circuited, so thereby this entire line is isolated, and now the transmission network is only one single line, so we have a still some power flow going on. So the maximum power transfer limits in each of these cases, that is before the fault, during the fault, and after the fault, will be different. So that's what we'll have to calculate in this. So finally, the question that is being asked is determine the critical clearing angle. So when the fault occurs, the rotor of this generator accelerates, and then at how much angle we should isolate the fault so that the machine still remains in synchronism with the infinite bus. So let's get started with that. So first, how do we solve this? So first we start by finding the current. So the current is complex power conjugate divided by voltage conjugate. So here the complex power is this one. So 0.8, and because it is conjugate I am putting minus 0.074. So this minus I am taking because of this conjugate. Then voltage here is just 1. So since angle is 0, so the conjugate also doesn't matter. So finally I am getting 0.8 minus J 0.074 per unit. Now I have the current. Now look at the total impedance between this and this. So first there is a generator. Generator itself has the internal impedance of 0.3, that is internal reactance. Then there is a transformer whose reactance is 0.2. Then I have two lines, zero point 0.3 and zero point 0.3, which are in parallel. So 0.3 and zero point 0.3 in parallel would be 0.15, and then total reactance xt will be 0.15 plus 0.2 plus 0.3. So this would be 0.65 per unit. So now I have total reactance. So from this I can find out, so I know the total current and total reactance. So from that I can find out what is the E dash. So E dash is nothing but the receiving end voltage plus the drop. So that is J into X total into I. So what is this? So I know the voltage is 1, and then the X is 0.65 J, and then the current is this one, 0.8 minus J 0.074. So once I do this calculation, so I will get the value of E1. So this value turns out to be 1.17 and at an angle of 26.387 degrees volts. So this is after converting into polar, I am getting like this. So the magnitude of E1 is 1.17, and then the angle of E1, that is this one, 26.38. So that means delta naught is 26.38 degrees. You can approximate to 26.4 degrees. And E magnitude is this. So now first I want to determine what is the Pmax 1. Pmax 1 is the maximum power that can be transferred when both the lines, the system is under normal operation. So that is EV by X. So E is 1.17 I know, and V is 1, and X is 0.65. So these are all magnitudes. So this turns out to be 1.8. What is Pmax 2? So Pmax 2 is when the line is under faulted conditions. So this is uh, maximum power limit under faulted conditions. So what happens during the fault? If I go up, so the fault is at the midpoint of this. So in other words, the fault is at the midpoint of this. So let me redraw this diagram now. So I have the generator. Its internal impedance is J.3. I'll just skip the J here, and then 0.2, and then I have one line is 0.3, and then the other line is 0.15, and this is a midpoint, and then 0.15. So this point is connected to the ground, and then the receiving end directly is your final bus. So under these conditions, so here I have EMF E, and then here I have the infinite voltage, infinite bus voltage, that is 1.0 angle 0 degrees. Now I want to know what is exactly the resistance between this machine and this one. So here you see this point is like a star connection. So I'll further simplify it. So this is E, and then I have a star connection of 0.5, and this side is 0.3, and this side is 0.15, and also there is a 0.15 here, and then finally I have the infinite bus. So this is where the fault has occurred. So this is my V infinite. Now this star connection I can convert into delta. So when you convert into delta, so this particular reactance, whatever comes between these 2 points, will be something like this. So 0.5 plus 0.3 plus 0.5 into 0.3 divided by 0.15. So that will be X total, that is between this point and this point. So if I say A and B, so between A and B, this will be the match. So this is basically star to delta conversion. So this value 0.5 plus 0.3 plus 0.5 to 0.3 by 0.15 turns out to be 1.8 per unit. So if this is 1.8 per unit, I can just redraw the drawing now. So this is E. There will be some impedance that we did not calculate. This is 1.8, and then this one I know is 0.15. This one is not required here. This is 1.8 per unit, and then finally I have the V here. So this is what matters when calculating the maximum power transfer capability. So that is Pmax will now be EV by X, which is 1.17 into 1 divided by this one, 1.8. So this is 0.65. So this we are denoting as Pmax 2. Next we have to find out what is Pmax 3. Pmax 3 is under after fault conditions. So when the fault is removed, the system is something like this. So this particular line which is there, this line is open circuited. Let me just show it as open circuit. So the circuit breakers on both sides open, and then this fault is isolated. So this is 0.3, this is 0.2, and this is 0.3. So this is E and this is V. So the total impedance now is just a series addition of this. So the total impedance is 0.8 per unit. So therefore Pmax 3 I can find that is EV by X. So that is 1.17 into 1 by 0.8. So this value will be 1.4625 per unit. So I have now three values. So let me diagrammatically show them so that it will become more clear. So this is under normal operations. This is P1. So the maximum value here Pmax 1 will be equal to 1.8 per unit. This is under normal operation. Now if I have a fault under faulted conditions, this is my Pmax. So the height of this will be, I'll just write it here. Pmax 2 is 0.65. That's what we calculated. And then the third curve that we calculated, it will have, this is after the fault is cleared, this point, that is Pmax 3, that is, we just calculated 1.46. And under normal operation, if I go to the question that is given, so the active power that is going is 0.8, that is given in the question. So because active power is 0.8, so at 0.8 I draw a line. So this is 0.65. So 0.8 line will be somewhere like this. Let me use a different color. So this is P mechanical 0.8, because electrical power, mechanical power will be matching. And we already calculated this angle, that is, this angle is delta naught. We already calculated that. So what is delta naught? So if I go up, so 26.387 degrees. 26.387 degrees. So when the fault occurs, so this is before fault, this is during fault, and this is after fault. Okay, so when the fault occurs, at the time I am operating at this point, at the time I jump to this point, and then mechanical power is more than electrical power, so the rotor will accelerate. So I keep accumulating this area and I'll keep moving towards the right. So after some angle, the fault is cleared. So let's denote this as delta C. So here I am assuming that the critical clearing angle is delta C. So that's what I want to find out. This is unknown. So then I'll directly jump to this point from this point, because now I am on this curve because fault is cleared. This red curve will be what is there. So mechanical power is still 0.8, electrical power is almost here. So this area will be my decelerating area. And when these two areas are matching, so maximum it will swing up to here. So that is delta max. And then it will come back. So delta max actually I can find out. So how to find delta max? Because I know this curve, so this is zero point 0.8 and this point is 1.46. So here it is. So from 1.46.8 I can do sine inverse. Then I'll get this angle that I have to subtract from 180. So first let me start doing that. So delta max will be uh, 180 degrees minus sine inverse of 0.8 divided by 1.4625. So this one I'll get something like 146.8 degrees, or if I convert into radians it will be 2.56 radians. So that is this delta max angle. So now I know, so this is 146.8. So I know this angle, I know this angle. So this angle I have to find out. And then I also know P1 max, P2 max and P3 max. So then we can actually solve it. So if I just quickly refer to the previous video which I have done. So this is the formula. So this is critical clearing angle. So here everything I know. PM I know. Delta max, PM is zero point 0.8. Delta max we just calculated. This also we know. P3 max, P2 max, all these things we know. So just by substituting all this, I'll be able to find the uh, solution. So let's do that. So I'll get cos of delta C equal to, it might help if I copy the formula. So let's try to do that. So here is the formula. So from this, I'll find out cos of delta C equal to, so PM is 0.8 given in the question, and delta max in radians it is 2.56 radians. Here I mentioned that, minus delta naught. Delta naught also I have to give in radians, so that is 0.46 plus P3 max we just calculated, that is 1.4625. Then cos of delta max. So cos of delta max, so cos of this 2.56 radians minus, so this minus is there. P2 max is 0.65. This is the maximum power during the fault, and then cos of delta naught, so 0.46. And this whole thing divided by, excuse me, this whole thing divided by P3 max is 1.4625 minus P2 max is 0.65. And if you calculate this, the answer turns out to be minus 1.53. And then, so from that, this is cos inverse of minus 0.153. So that will be 98.8 degrees. So this is the critical clearing angle. That means if I clear, so this one we solved it 98.8 degrees. So if I clear the fault before the rotor reaches 98.8 degrees, then the synchronism is maintained. Otherwise, synchronism is lost. So basically, this is a numerical example to show how to use the equal area criteria to determine whether the machine will be stable or it will be unstable. So I hope you got something from this solved example. So so with this we kind of conclude our study of equal area criteria. Thank you.